I'm going to try and stay on time. Good morning, everybody. Thank you for coming. I'm going to give a broad overview talk today about quantum computing. And what I want to do, I'm going to start off with a meta question, which is not to explain to you how quantum computers work per se. Instead, I want to talk a little bit about the question of how to explain how quantum computers work. In particular, there's a reason for this. How many people here have read sort of an article about quantum computing where they talk about the computer being in many different states at once, or the quantum bit being in many different states at once, this kind of thing as being the... Okay, so nearly all of you, which is or many of you, which is what I expected. But basically what I want to do to start is to explain why this is misleading, why it's the wrong way to think about quantum computation. And to do that, we need to think a little bit about explanation, and in particular, a subtlety about explaining quantum computation. Uncontroversial statement that we certainly like to understand new ideas in terms of other things that we already understand, and the more such relationships that we have, the better we feel we understand those concepts. So certainly one of the first sort of aha moments for me in my life, I can't remember how old I was, about probably 6 or 7, was reading about atoms, which are quite an abstract sort of an object, but you get a sort of a basic picture. You have this heavy nucleus which is surrounded by electrons, and then you start to refine that picture. You discover that it's not just orbiting electrons, but you've also got the nucleus has structure, and then you keep sort of moving ever onwards, building up a more refined picture of the atom. You can keep going sort of essentially, well, not quite forever, but there are many layers that we have. So we're adding layer upon layer to our understanding, coming closer to a complete understanding. But the interesting thing is that this original picture, while it's not the complete truth, it is a partial truth. When you learn that picture, you are actually gaining some sort of understanding of what's going on inside an atom. It's very tempting to pursue the same kind of strategy for understanding quantum computing. Basically to look for some kind of concrete explanation, like the electrons, little balls of charge orbiting a very big ball of charge, to understand quantum computing in terms of things that you already understand. It's tempting, but it's extremely dangerous. So imagine that I am able to give you a very concrete model, a direct concrete model of quantum computation. Like, for example, this one that says the computer is in many different states at once. And that's what's really going on. So sort of, I think of these as kind of cogs and pistons type of a model, but it could be anything. There's nothing sort of special about that. This would be very satisfying, like the parallel worlds or the many simultaneous states explanation. But there's a very big problem with it, and the problem is this. If the concrete explanation I give you is really truly accurate, if it was perfectly accurate, then it should be possible to efficiently simulate all of the classical elements, because that's what we think about, of that explanation on a conventional computer. And that would mean that we could efficiently simulate a quantum computer on a conventional computer. The reason, of course, that we want to understand quantum computers is in the hope they can do things that conventional computers can't. So what's really interesting about quantum computers is, in fact, the gap between my ability to give you a direct, concrete model of how they work, where there's a one-to-one correspondence between the elements of the computer and the elements of the explanation, and what's actually going on. So I like to call this the quantum gap, for obvious reasons. And what it means to understand quantum computing, in some sense, is to build bridges across that quantum gap. So I'm going to do a little bit of that later in this talk. So if you go about understanding in the standard way, if you build up this concrete model, you'll miss the gap completely. Okay, I've actually said that. Okay, so I've started this talk by saying, here's a way of not going about understanding something, which doesn't seem very necessarily particularly helpful. You've kind of, I hope, have lost some hope of understanding in that way, which is our traditional way of understanding abstractions. But you've also gained something because I named an object for you to look for. I named, look for this quantum gap through the rest of the talk. That's what you should, in some sense, be focusing on. So last night, basically I changed my talk around quite a bit. I spent a lot of time preparing the talk, and then last night and this morning decided to change it quite a bit. My original plan, let's see how this, oops, I'm having the traditional mouse pointer. Here we go. My original talk, basically what I do from here is I explain actually the whole quantum computing model in 10 minutes. I don't mean, it's not a vague hand-wavy sort of explanation, actually the real model, the quantum mechanics and all. Can I ask for a show of hands, how many people here have taken sort of half a dozen or so mathematically oriented undergrad subjects or have done the equivalent study? So if you're a physicist or a mathematician, okay, a pretty large fraction. What I was considering doing, this is a broader audience, a more diverse audience, which is fantastic than I had originally expected. I will go through that model. It's sort of an interesting fact about it. I'm going to dump a bunch of mathematics on you, not complicated stuff. If you're not that comfortable with it, just take an impression away. You don't need to actually worry very much about the details. What I'd really love to do is to have an hour in which to explain that model. Basically, I can explain the whole model in 10 minutes, but to get all sort of hooks into your other understanding takes somewhat longer. I don't think there's anybody who can give you a really good explanation in less than 10 minutes that makes all those sorts of hooks to your other ways of understanding things. Then I'll talk a little bit about what quantum computers are good for and what quantum computing might potentially have to do with the singularity, and I'll try to get to those other questions down below later on. Okay, so the mathematics of quantum computing in 10 minutes, or maybe a little less. The explanation is complete. There's not, I'm not leaving anything kind of in reserve in some sense. You'll know everything about quantum computing in the same sense as knowing the Maxwell and Lorentz equations. If I just write them down, you know everything about classical electromagnetism. It's true, but you've got to do a little bit of unpacking, preferably through a few thousand hours of extra study. I'm going to do it once and then I'm going to summarize it, so don't worry if you miss a detail. You'll see it again. So what I'm going to do is I'm going to explain the quantum circuit model, which is like the classical circuit model for conventional computers. It's very, very similar. It's certainly inspired by, in many ways, directly parallels that model. It's not the only model of quantum computing. There are many other ways of describing quantum computation. Some of them sound very different than what I'm going to describe. They're equivalent, though. So in sort of a formal mathematical sense. So you don't learn anything new by going to those other models in some real sense. Although, of course, from a sort of a psychological point of view, it may give you some advantage in trying to come up with new algorithms or new ways of doing quantum computation. But sort of purely in a formal sense, what I'm going to describe for you is enough. Okay, it's an abstract model of quantum computing, by which I mean it's not actually, I'm not going to talk about atoms or photons or any of the sort of the real world objects. I'll talk a little bit later about physical implementation. It's not hard to understand how the model works. It's just a few simple lines of equations. It is, however, difficult to understand why the model works. If you try and sort of master the model or ask yourself why are things that way, you quickly go down a bit of a rabbit hole. I could try and explain it, but I'd be condensing 90 years of understanding, which is still only partial, into my 10 minutes, and I simply can't do it. I'm going to have to ask you to take it on faith that the model does make sense. The model is simple, but not easy to understand why it's true. I'll quote John von Neumann, who said, in mathematics, and I might add in physics, you don't understand things, you just get used to them. The model has a little bit of that flavour. Of course, I mean, the additional thing is you do try and build connections to other things that you know, and that's in my belief anyway, is that that's where the understanding arises. Okay, so the quantum analogue of the bit is called the qubit, not surprisingly, the quantum bit. So I've drawn sort of an abstract representation of three of them here. We're going to imagine a computer with n qubits when we need sort of the of course, classically, they all have, you can describe the state of a classical 3-bit computer by 3 bits, 0, 1, 0. A quantum computer is quite a bit different. A state, it's not just a single number, 0, 1, 0. Instead, it's a whole collection of many different numbers. That's what we mean to describe the state of a quantum computer. In fact, it's a collection of 2 to the n numbers, so it's going to be 8 in this 3-qubit case. A very conventional piece of notation is psi, and here you have sort of, the eight numbers, which psi is kind of, it's a placeholder for those 8 numbers, and you'll see that I've labelled them, the 8 numbers, by all of the classical 3-bit strings, 0, 0, 0, down through 1, 1, 1. So these numbers are called amplitudes. They're typically, well, they're complex numbers. So here, what I've shown you is I've shown you the state of a 3-qubit quantum computer. So we label the whole collection by psi, and this is what psi is made up of, is these 8 numbers. And that's it. That's a perfectly good 3-qubit quantum state. In fact, you could make that using existing technology. Yeah, we'll come back to that a little bit. Okay, so there it is. Most important fact, in some sense, the quantum state is not directly accessible. What do I mean by that? I mean that if you actually had that state in the lab, it had been prepared, it would not be possible to read out all of that information. There would be no way of extracting it. In some sense, there's kind of hidden information in there, all those so-called amplitudes, those complex numbers. It's only possible to get very partial information about the state. That's tremendously important. In some sense, it's hidden. When you measure the computer, when you do an observation on it, what you get instead is you don't get all that information. You get a single one classical bit string. You're going to get 3 bits of information out. So you might get, for example, the bit string 111, and that occurs with a particular probability, which is just given by the corresponding amplitude squared. So in this particular case, because the amplitude was square root of 0.6, it's just going to be 0.6. And you can see where sort of one of the main rules, well, really the only rule for quantum states comes from, which is that the sum of the squares of the amplitudes must be 1, because the sum of all the different probabilities for all the different possible outcomes must be 1. So that's everything you need to know about quantum states. That's it. You can start to see already where the quantum gap comes from, because if you have n qubits, which physically we're going to just, is going to be implemented in the laboratory using, say, n atoms, so 3 qubits will become 3 atoms. But mathematically it's described by 2 to the n different amplitudes. Well, 2 to the n is typically much, much, much bigger than the n atoms. There is no direct correspondence from one to the other, which is reflected in the fact that physically we actually can't directly, we don't have direct access to those amplitudes. There's only an indirect correspondence, and this type of indirect mediation, it doesn't matter how you describe the quantum computer, so there are other ways of describing it apart from using amplitudes in this way. But indirect mediation seems to be an essential part of understanding quantum computers, no matter how you describe it. This is related to, if there wasn't some indirect mediation, we'd be able to do the simulation on a conventional computer, and quantum computers would not be so interesting. Okay, so I've told you how to describe the general state of a quantum computer. Of course, we need some starting state, and I'll just say that there's a convention, which is you imagine the computer starts in the all-zero state. Now, that's a classical concept. What does it mean? It just means that the amplitude for all zeros is 1, and all of the other amplitudes are 0. That's all it means. So that if you measured the computer, you'd get all zeros with probability 1. Okay. I asked Michael if I could have a fair bit of time for questions. The talk is in some ways a little bit technical, and people are not typically familiar with quantum stuff. So I'm just going to pause for a few minutes. If anybody has any questions that they want to ask up to this point, please feel free to come forward and ask them. I can take up to 2 or 3 questions. If there are no questions, I'll move along.
You said you could simulate quantum computers on a classical computer, but can you simulate the collapse?
So you can't, well, as far as we know, you can't simulate them efficiently. You can simulate them very inefficiently. Can you simulate the collapse? Sure.
Assuming it's random, so you're discarding the Penrose possibility.
No. So, I mean, to do the simulation of the randomness, I just use a random number generator.
So if you assume it's random, you could simulate the collapse.
Sure, absolutely. Yep.
Could you talk a little bit about the relationship between what you showed us, the bit states, and the idea of consciousness, the quantum consciousness, which was just talked about? Do you think you could comment on that?
Well, it was a general question asking how to relate what I just said to your well, actually, what I'm going to do is I'm going to dodge the question right now.
Should be.
Thank you. So I'm going to dodge the question right now. Actually, what I should have said before is during the talk, the main body of the talk, I'll pause a couple of times. I'll just ask for questions which are directly related, and then general questions at the end. From now on. In terms of the connection to consciousness, what I will answer your question since I hadn't made that caveat. The connection to consciousness, I mean, in what I've currently said, as far as I'm aware, none. Okay. Stuart, if you want to comment on that at the end, you go right and feel free. Okay, so that's how you describe the state of the computer, and hopefully that was clear. All right, so the state alone is not enough. You also want to be able to describe the dynamics. It's got to do something, right? And so we're going to have quantum gates, just like classical logic gates, that manipulate the state of the quantum computer in much the same way as classical logic gates, like the NAND gate or the AND gate or the NOT gate or whatever, manipulate the state of classical computer. In particular, we're going to find that any quantum computation can be built up by a set of so-called universal gates. And I'm going to describe a very simple set of universal gates, much as any conventional computation can be built up just from NAND gates, for example, as many of you are probably aware. So I'll describe a universal gate set for quantum computers. You can actually give, like for classical computers, you can write down single gates, like the NAND gate, which are universal for quantum computation. It's a little... They're really ugly, though, so I'm going to describe 3 fairly easily understood gates instead. So I'll start with the pi over 8 gate. These next 3 slides are the most technical, so if you get a little lost, don't worry too much about it. So there's a so-called pi over 8 gate. It's a single qubit gate, meaning physically, if we've got our 3 blobs, maybe it's 3 atoms, we're just going to do something to one of those atoms, say the second of the atoms in this example. And what happens is it changes all of the amplitudes. And here's the rule that's used. So the amplitudes where the bit string... okay, so the amplitudes where the bit string has a 0 in the middle and whatever at the start and whatever at the end just get multiplied by this number, e to the minus I pi over 8. And the amplitudes with a 1 in the middle get multiplied by e to the I pi over 8. So a different sign, it's a different number. And that's it. That's all that happens. Very, very simple kind of a gate, and I trust you can see why it's called the pi over 8 gate. Okay, so these are just a couple of examples of where I've filled in the wildcards, the stars. Okay, so that's one gate. Very simple gate, the pi over 8 gate. The second gate is the controlled NOT gate. This is actually a conventional classical gate in some very real sense. All it does, it's a two-bit gate, so you have 2 inputs, x and y, and all that happens is, so x is left completely alone by the gate. The y bit is just flipped if x is set. That's all that happens. Very simple gate again. Okay, so that's the classical description. I need to give you sort of a quantum description of it. And all it does, it just permutes the amplitudes according to the same rule. So to write that a little bit more formally, if it was the first 2 qubits in our computer, these amplitudes, psi, x, y, anything, would get turned into psi xy plus x, anything, right? And the third and final gate is the Hadamard gate. I'll imagine I'm applying it to the first sort of 3 qubits, just to be, it's a 1-qubit gate again. And here's the rule, the 2 rules, and that is that the amplitudes which start with a 0 and anything after it get changed into this sum of the corresponding amplitudes with a 0 and a 1 and a minus sign here over a root 2. And very similar kind of a rule for amplitudes where the label starts with a 1, except there's a plus sign instead. It's the only difference. Right, so this is very, very simple rules. You actually pretty much understand everything about quantum computing at this point. You can see the quantum gap, by the way, just as we saw before. Where we see it is that we have a single physical operation which is remixing all 2 to the n of the amplitudes, right? It's incredibly complicated remixing. If you actually write it all down, it does an amazing thing, but you're just doing one thing physically, so there's no direct correspondence between the 2. This is part of the key to the power of quantum computing. Okay, so I just want to summarize the model and fill in a couple of little gaps. So you have n qubits in your computer. Here's the n equals 3 case. Described by 2 to the n complex amplitudes. We usually use the letter psi. 1 amplitude for each n-bit string, so psi 110 is a typical one. It's a complex number. You can't measure the amplitudes directly. That's absolutely key. You can only get indirect information by measuring bit strings. The probability of a particular bit string is given by the amplitude squared. The sum of those is 1. It starts in the all 0 state, which means psi 00 is 1. A computation is just a sequence of gates chosen from those 3. And this is the bit I left out. At the end of the computation, so after you've done all of your gates, you do a measurement to get an n-bit output, so a 3-bit output, for example. And that's the output of your computation. That's it. That's all there is to quantum computation. You know Maxwell's equations. If anybody can come up with a new algorithm by lunch, I'll be very impressed. Okay, so let me just pause again for a couple of minutes to ask if there are any questions. Okay, so we will have a couple of questions. Sorry? This is not the end. I have more to say. This is the basics, right? I want to give you a real picture of what's going on in a quantum computer. This is actually what it's about.
All right, so a gate modifies all the 2 to the n size at once.
That's right.
In anything like practice, would your quantum computer be broken up into something like words so that n was only like 16, or would like the whole 64 meg of the computer be used as 1 2 to the 64th word?
Okay, so there is no way, the quantum description, there is no way of escaping using all of those amplitudes. If you've got, 64 million, separate qubits, you're going to be manipulating, when you just do one gate, you are effectively going to be manipulating 2 to the 64 amplitudes.
So you wouldn't make a computer out of smaller blocks. It's just going to be this big thing.
Well, I mean, the point is, right, from your point of view, you're just going to have the qubits. You're never going to see the amplitudes. That's bookkeeping. It's an amazing sort of bookkeeping job that nature is doing. There are alternate descriptions possible which don't involve the amplitudes, but so far as we know, they all seem to involve this amazing kind of blow up. It's not well understood. It's a great question.
Oh, thank you.
Okay. All right. We'll keep going. I'll quickly whiz through what are quantum computers good for. Basically, all of the sort of general articles that are written, they all give you the same answer, and there's a good reason for that. We don't know very much about the answer to this question. So I just want to remind you what we know, basically to stimulate questions at the end. So they're good at finding prime factors of very large numbers. Okay? So if you have an n-bit number, a 1,000-bit number, for example, roughly speaking, the amount of time taken on a quantum computer is 1,000 cubed. Actually, there's a slightly faster algorithm. It's n squared log n log n. But anyway, that's the basic point. On a conventional computer, the best known algorithm scales exponentially. hope this is clear here. The key point is that you've basically got an e to the n. So what happens is if you're out at 1,000 bits for the number you want to factor, well, when you add an extra bit, n cubed, that extra time goes up by, I guess, about a factor of 0.3%. Whereas e to the n to the 1/3, blah, 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 I won't try and work that out, but it goes up by, by a lot more. I mean, each extra thing that you add on more or less doubles the computation time. Right? So it gets dreadfully complicated, very, very difficult. Very, very dreadfully slow, the best classical algorithm, very, very fast, as the size of the number to be factored gets larger. And part of the reason, I think most of the reason really for the funding for quantum computing and much of the interest from funding agencies is that this problem of factoring turns out to be a way of breaking the public key RSA algorithm, which is very widely deployed. It's deployed in web browsers and in many other applications. Okay, so that's number one. The second sort of big thing that we know is that if you have an n-item search space, well, classically, if you want to search it and there's no structure, it takes you have to search the whole space, all n items, typically. It was like having an unordered telephone book. But quantumly, it turns out that you can do it in time roughly root n. So you get this amazing sort of quadratic speed up. You can prove actually that you can't do any better than root n. So just to give you some idea of how one might use this in practice, if you had a travelling salesman problem on m cities, so you wanted to do a search of all of the different city routes potentially, so m factorial city routes, you could do it in time roughly the square root of m factorial instead of having to search all of them. Now, unfortunately, this is not necessarily useful if there is structure which can be exploited in the search, and that's certainly the case, for example, in the case of travelling salesmen. There are smarter ways of doing it than simply searching every single possibility. And the third sort of standard generic application is simulating quantum systems. So quantum systems turn out to be very difficult to simulate for the reasons I've already described on a conventional computer. There are a limited number that can be simulated quickly, but generally there's an exponential slowdown if you want to simulate even very modest-sized classical quantum systems on a conventional computer. It's because of this quantum gap. So quantum computers are very good, in theory, at simulating these systems, and in theory, at least, should be good, therefore, at designing, potentially have applications to the design of new materials, or maybe designing new drugs. This is all widely believed. Unfortunately, it's not something. The proof of the pudding is in the eating. It hasn't actually happened yet, so we have to wait and see whether or not that will indeed be the case. I certainly believe that it's true. Keep going. All right, so here's the question that I guess is most related to this event. What's quantum computing got to do with the singularity? I have many thoughts on this. I'll give you two. Thought number one is really its prelude to the second. The thought is this. We humans have a very poor understanding of quantum mechanics. We don't really know how to think about it. That's part of the reason why there's very few sort of interesting algorithms. And you can tell a story about it, the sort of story that evolutionary psychologists like to tell, which is to say it's because our ancestors wouldn't have received much advantage from it. We live in a classical world, so why evolve to understand a quantum world? And one might hope that maybe a quantum AI will actually be able to develop a decent understanding of quantum mechanics. Maybe it's its native tongue, so to speak. Maybe you'll even be able to explain it to us in a way. Here's the second thought, which is really prelude for, and that is that we may have sort of a very interesting bootstrap, which is that conventional artificial intelligences may be the first to be able to build or at least take full advantage of the first quantum AI. So they may create the first quantum artificial intelligences. And the key point about these quantum computers, even though we don't have many algorithms for them as yet, we do have some suggestions or some idea that maybe they can solve problems exponentially faster than classical computers. So in other words, in some sense, they're operating in a completely different regime. right? For them, there are problems which are tractable, which are simply, unimaginable to do on a conventional classical computer. So a quantum AI may be a qualitatively different beast to a classical AI. It will simply have completely different reasoning powers. And one can imagine a second singularity in which the first wave of artificial intelligences, which are conventional, create a second wave of quantum artificial intelligences who they have absolutely no hope of ever understanding. Right? I mean, it would be an amusing situation. Something very much like that. I mean, you can sort of tell a similar story potentially about the ordinary singularity, if I dare use the adjective ordinary, in that connection, which is to say, well, sure, a few hours after the singularity has occurred, computers will be absolutely we will not be able to comprehend what they do. But several hours after that, the new computers won't be understandable to the first set. So it's kind of similar. We can be continually having little mini singularities. But this would truly be very different, potentially, if we can actually find interesting new quantum algorithms. Okay, so just to come back to the present day, the question that certainly I most frequently get asked about quantum computers when I tell people that I worked on it, is when will we have large-scale quantum computers? The answer to that question is I don't know. Progress is it's interesting to look at progress. It's basically like the 1930s, as far as I can see, with ordinary computers. There are some key bits of infrastructure or key bits of technology needed to make things scalable which are not yet available. So you can build simple logical devices. How many qubits we can perfectly control? I once asked, certainly one of the world's leading experimental quantum physicists, how many qubits can you perfectly control? He'd done some very impressive experiments involving quite a few qubits, and he said 0 immediately, which is a fair enough statement. I think even if you're a little less modest, we do have very good control at sort of the few qubit level, but that's it. Near perfect control of 1 and 2 qubits, and pretty good control a few qubits beyond that. Different people make different claims. To some extent, that reflects actually more about the personalities of the people involved than it does about the science in some occasions. It's not always true. I mean, it's a slightly unfair statement. I'm exaggerating to get the point across, which is, that people have interesting incentives in terms of what they report. The most interesting thing about quantum computers, because it's an abstract model of in relation to this question, because it's an abstract model of computation, you're not limited to any one technology. So probably the biggest funder in the world has been the US intelligence services in different ways, DARPA and NSA and whatnot. A few years back, I did a count of how many different groups they were funding. It was in the low 70s. And what was interesting was that a huge fraction of those groups were pursuing different technological approaches to quantum computation. So there's sort of many, I was going to say thousands of ways of skinning a cat, but I guess maybe 70 ways of skinning a cat. So all of those have to fail if we're to get blocked, which is interesting because it seems that each one has different sort of strengths and weaknesses. So they all have to fail, and it's kind of like whack-a-mole, as was being discussed this morning. They all have to fail, but they're going to fail for potentially for very different reasons, because actually, in some sense, we already have all of the capabilities we need to do scalable quantum computation. The problem is that they're not all in the same system, which is, sounds sort of like a facetious remark, but if you actually look at what's going on, people are hybridizing the systems. So for many years, probably the best technological approach, and arguably still the best technological approach, is the so-called ion trap quantum computer. So basically you take single atoms, which are ionized, you cool them down inside a trap, so that you're using electromagnetic fields just to arrange them, typically in a line. right? And then you use lasers to manipulate these atoms, and they can talk to one another because they're charged. And what actually, you think about this, and there are all kinds of problems with it. One of the most interesting things that's happened in just the last few years is they've started to integrate this with much of the semiconductor technology which has been developed and which is, of course, enormously scalable over the last 40-odd years, 50-odd years now. So they're sort of taking different systems, different pieces of different systems, and combining all the best bits, hopefully into hybrid systems that won't have any weaknesses at all. So I'm hopeful that things are going to turn out well in the near future, but it's hard to say. Okay, so I think at that point I'll pause, or I'll stop, in fact. Thank you all very much for your attention, and take some questions.
Hi, this is Ray Kurzweil, and I thought that was the clearest description of quantum computing that I've heard.
Thank you.
So congratulations on that. I'll comment in my talk, which I think is at the end of the day, whether or not I feel we need quantum computing for Turing test level AI or the singularity, or at least the first singularity that you talk about. To give a preview, I don't think we do. Do we need it for consciousness? That's a more subtle question, and I'll think about that for the rest of the afternoon and let you know what I come up with. I have a question on your last point on the feasibility and progress in quantum computing. The power of a quantum computer scales up exponentially with the number of entangled qubits. So if you add one qubit, you're doubling the power of the quantum computer. If, however, if the engineering difficulty also scales up exponentially with the linear addition of qubits, you're not getting any additional scale. In other words, if it's twice as hard to create a quantum computer with one more qubit, then you might as well go the classical route. And so far, looking at the field, it's appeared to be that way to me, but I wonder what your feelings are on that.
So, I mean, it's a very interesting, I mean, of course one can't know. My feeling is probably that's, I can't prove it, but I think that's likely not to be the case. What's going on there is fundamentally problems. To go back to a classical analogy, it's like we were in a situation where, you were having a lot of trouble building wires, building NAND gates, and just building stable bits, right? And so you kind of have to use duct tape and whatnot to get 3 or 4 or 5 of these things together. The technologies which are required for scalability have simply not been there at all. And so when you look and say, oh gosh, we had 4 qubits for such and such a period of time, now we've got 5, and that took an extra 3 years or something like that. Well, that's an exaggeration, but it took another year. Isn't it just going to continue on like that forever? But that's not the right way of looking at it. What's actually happened is they've simply found better duct tape, right? Meanwhile, the development of technologies which do scalable, for doing scalable stuff, that's chugging along completely independent, but it didn't actually get involved in that, it wasn't involved in going from 4 to 5 qubits. So I think we're sort of seeing separate or parallel development of technology, and what you're seeing is simply that duct tape is very hard to apply at scale. Yeah, sorry. Okay, thank you.